Hello everyone, today we are going to study polarization. First, we will start defining polarization and describing its methods, and then we will sketch and analyze the diagrams which showing that polarized, transmitted and reflected beams. And finally, by using Malisson's law, we will look at how the intensity of light beam has changed when it passes through a polarizer. So let's start with defining polarization. Polarization is an incident caused due to the very nature of electromagnetic radiation. Well, alright, how we can polarize light? Especially these days, the weather is too hot, the city is burning because of sun. And especially at noon, we can't even open our eyes. So, because of the sunlight. So, what is the solution here? It's quite simple. Wear a sunglass. When I put my sunglasses on, the light in the classroom is filtered by the sunglasses. So the classroom becomes dark for me. Before move on the methods of polarization, let's look at how a light wave travels. Light is an electromagnetic wave which oscillates, as you can understand from the name, that electromagnetic waves consist of electric fields and magnetic fields. So these electric and magnetic fields are oscillates all the time and change over time, and they are always perpendicular to each other. Something like this. If these ones are electric fields, to the upward or downward. These are the electric fields. I know that it's not an easy job to draw on a two-dimensional plane, but you can imagine that this one is three-dimensional. The black ones are electric field and the red ones are magnetic field. And this is the direction of propagation. When we put aside the magnetic field now and focus on the electric field, it will make easier for us to understand the topic. So, if this ray is coming directly to the observer, what does the observer see? Let's draw an horizontal and vertical line here, two axes. So, this point where these two axes are intersects corresponds to the axis of propagation of ray here. So when we look at this vertical line, we will see that electric field is up and down. Here, the electric field is up and down here. So the electric field will be up and down. The observer see that the electric field, the coming ray, is up and down. So and we call this kind of polarized light as linear type of polarization, and we call the light here. So this might be also something like this. It could be horizontal, it could be also orthogonal. So we call that if the electric field of a light ray oscillating only in one orientation, only one direction as polarized light, we can call this linear polarization of light. So how about unpolarized light? Most of the time the light coming to us is unpolarized. For example, the ray of sun strike directly to us is unpolarized. Or let's take a look at electric light bulbs. Let's imagine that we have an electric light bulb, something like this. So the rays come out from the light bulb is in all directions, and they are at the same time in overlap, and they are overlap each other. So if we want to draw the diagram of the situation in our horizontal and vertical axis, it should be like this. Some of them will be orthogonal, some of them will be up and down, and some of them will be left to right. This is the case when the light is open, when the light is turned on. What I am trying to explain here is that we cannot know in which direction electric fields from a random source come out in our eyes at any given moment. So this is the diagram of unpolarized light. Let's imagine that, let's say we need a polarized light for our experiment. So the solution is quite simple. We can use a polarizer. These materials are made of glass and plastic. This one is plastic, for example, this one is glass. And they are allow light only in a certain direction. They have their specific properties. So if we want to have a vertical direction of the light, let's imagine that we have an unpolarized light here, and we put a polarizer here, which is vertical direction. Polarizer or filter. So if we put unpolarized light from a random source into a polarizer which is vertical direction, it allows only vertical direction of the light. So we will have a light in only vertical direction. Something like this. So let's take a look at circular polarization now. If we go back here, we have the electric field was up, and let's say we send another ray not in the same direction, and let's polarize like this, just like magnetic field, but this is, be careful, this is completely a different beam. It has its own polarization and own magnetic field. So what do we expect to happen when we look at these two rays from the right side? When we draw our diagram and look at these two rays, we see that the electric field of the first one was up, like this, and the other component towards left. So the direction of the total electric field of these two rays will become like this. And if you want, we can also calculate the magnitude of this resultant vector by using Pythagorean theorem, but for now we are only concerned with the direction. And this one keeps happening over and over again, and finally we will have a cross-polarized beam. And finally we will have this cross-polarized beam. Actually, this is nothing new to us, but if we shift the second ray we send right now, if we shift, it is for 90 degree. If we shift 90 degree, so we got something very interesting, and what we are going to find is not going to be linearly polarized. So let's reconstruct our diagram for this one and look at these two rays from the right side again. We see that because the observer is here, so we should look from right to left. So in this point, the electric field of the second ray was maximum. As you can see, the electric field of the first one is minimum. So that means that this is this point. And the second point, we see that the electric field of the first one is maximum and the second one is minimum. So it should be something like this. Let's say this one is A, B, and the other one, the third point, we have the electric field of the first one is maximum and the other one is minimum. And it should be also like this. This is point C and this is point B. So we see that the polarization of these two rays rotates clockwise. It was from here to here, here, here and here. So the polarization moves in a circular path. So why we call it circular polarization. Circular polarization. In this type of polarization, while the light is coming toward our eyes, the main polarization angle turns slightly. So we don't have to keep our head horizontal all the time when we are watching 3D movies. And finally, if the phase shift is other than 90 degrees, the polarization shape becomes elliptical. So the light is elliptically polarized, and this is the last type of polarization, the elliptical polarization. And today we'll look at the types of polarization. First we'll start defining the linear polarization, and afterwards we define the circular polarization, and finally we said if the phase shift is other than 90 degrees, it was elliptical polarization. And you can also see the shapes here. This one is linear, this one is circular, that is we have two rays here, and also in elliptical we have two rays, but the phase shift is other than 90 degrees. This was linear polarization, the circular polarization, the elliptical polarization. Right now there is a very short video I want you to see. This is the time, the propagation axis. We have two. This one, the red one is electric field and the blue one is magnetic field. As you can see, the green one is the resultant vector. And this is become linearly polarized because there is no phase shift. The phase shift is zero between these two rays. But as you can see, the phase shift is by a quarter cycle. Quarter cycle means pi over 2, which is 90. When the first ray is minimum, the second ray is maximum, as you can see here. So the green, the resultant vector, moves and rotates counterclockwise this time. And right now, let's look at the methods we use in polarization of light. First, which is the transmission, reflection, scattering, and refraction. So let's start with the transmission of polarization. This one, the first one is the transmission, which is the regular one. We just put a polarizer in front of a source, the light source, and then we will get what the polarizing filter gives us. If, for example, this one is a vertical direction polarizer. So the second one is a reflection. The unpolarized light coming through to the air, and we have this air and glass. So when the sunlight interacts with the surface, some of them will be partially polarized and the other one is partially polarized and inside to the glass. This is a type of reflection, the methods that we use. And the other one is scattering. In scattering, usually we will see some rainbow and stuff by this method. And in this method, when the unpolarized sunlight is coming through and shakes the molecule, the air molecules, some molecules were in the air, so some of them will be polarized and some of them will be again continued transmitted unpolarized light, and some of them partially polarized light. So this is a method that we use polarization by scattering. And finally, refraction, polarization by refraction. In this type of polarization, we have the optical active substance between the source and the analyzer. We have this polarizing filter and analyzer filter. So when we put an obstacle, a substance which is optically active, so afterwards we see that some of the light, the direction of the coming light will be changed, and we see that on the screen. And this is the third method that we use in polarization. And finally, let's look at Malus's law and calculate a problem. This is a typical type of polarization we use. We have this polarizer filter, and this is the unpolarized light. We know the diagram for now. And we have this analyzer, which is makes an angle between the polarization axis and the analyzer. So the formula is I is equal to I0 cosine square of theta. So here I the intensity of the light, and I0 was the initial intensity, and this is the cosine theta. This theta is, we just mentioned, the angle between the analyzer and the propagation axis. So we have this problem. We have two polarizing sheets. These are the filters together, and the angle between these two is 37. And finally, we are looking for the initial intensity given as 300 watt per square meter, and we are looking for the final intensity of the light. So let's first write the given information in the question. I0 was 300 watts per square meter, and we also have this theta given as 37 degree, and we know that the cosine theta is equal to cosine 37 0.8, and we were looking for the intensity of light, and by using Malus's law, I is equal to 300 times 0.8 square and 300 times 0.64, and that's equal to 192 watt per meter square. If you have a question, please don't hesitate to ask.